All right, we're down to our last presenter of the day. So our next presentation is on the effects of bridge construction on overland erosion and downstream sediment regime. Our presenter, Dr. Habib Ahmari, is an assistant professor in the Department of Civil Engineering at the University of Texas at Arlington, UTA, and a licensed professional engineer in Texas and in Ontario, Canada. He has more than 20 years of industry research and teaching experience in the areas of water resources, environmental hydraulics, and river morphology. Before joining UTA, he worked for 10 years in Canada, where he had led several environmental impact assessment studies of hydroelectric dam construction projects. Let's please welcome Habib. Thank you.
Thank you, Eric, for the introduction. I was thinking why I'm here. This is a drainage session, but I'm glad you are here to listen to my presentation. Thanks so much. So today, my presentation is about the toolbar, GIS toolbar that we have developed for TxDOT to predict the effect of bridge construction on overland erosion and the sediment regime downstream. So the work is done, the toolbar is completed, but I have to have the disclaimer here that TxDOT has not utilized it yet because we just tested at one site, but in the next phase we are going to do more validation. The work has been done with my collaboration, my students that are graduates, Sam and Matthew. They basically did the modeling part and are presenting their work. So this is the background information I'm going to talk about the overland erosion in general and what would the effect of the bridge construction on overland erosion and sediment regime. We're going to talk about the theoretical background of the model. I promised you that I'm not going to go over the technical details here. The interface of the model, and then the field data we have collected to validate or at least evaluate the performance of our model. So, just a little background. As you know, we have more than 600,000 bridges in the US. 85% of these bridges are crossing a water body, either a stream, creek, or river. And then, whenever you're building a bridge, obviously you bring the equipment, you're just disturbing the soil, removing the land cover, changing the elevation, and a lot of activities going on, and all these activities will contribute to overland erosion when there's the rainfall during the construction. And this sediment would enter the channel and would go downstream. So the reason that TxDOT wanted to have this research started is that what is the impact of this sediment on the aquatic habitat downstream, with the specific focus on freshwater mussel. In United States, we have 70% of freshwater mussels species are considered be at risk. In Texas, we used to have 15 of them listed as endangered species. Now we have added another one, so we have 16 species endangered and listed as endangered. So this sediment would cause some issues with the all habitat, including freshwater mussels, that could be basically bury the mussel, causes some issue with the respiration and limiting their habitat. When we started doing this project, we couldn't find a one-step or one-shot model to do all this work. Look at the hydrology, come up with the overland runoff, calculate the overland erosion, run the sediment, run the hydraulics all at the same time. There are some models out there do one or two of these type of work, but not just single model. The other thing is that the footprint of the bridge construction is very limited compared to the watershed scale or sub-watershed scale. So we needed something simple that the TxDOT employee or other DOT employees can use it without learning about the new model, without running the model through the calibration validation process, something simple that would be very practical for practitioners. So in terms of the limit of the construction impact downstream, there is a requirement for many entities, DOTs and other state governments, that you need to basically do some surveying for, this is specifically for mussel in this the presentation, but generally if you're doing the construction, you have to have some monitoring to figure out where the mussel or the habitat would exist. In Texas, they're saying that you have to do the monitoring within the actual footprint of the project, 50 meters downstream, 50 meters upstream, and then if there's a mussel, either you have to relocate them or probably do some mitigations. Where these numbers come from, I have no idea. I asked the question, they have no idea. Maybe they pull out from the air. But that criteria would change from state to state. If you go to Ohio, they are talking about 10 to 50 meters upstream, do the surveying, and then 25 to 100 downstream. In Virginia, 100 to 200 upstream, 400 to 800 downstream. In Georgia, 100 upstream, 300 downstream. So the question would be, is it adequate? In some cases, are we doing too much of surveying or too little? So we are spending resources, but we don't know if you are getting the accurate extension of the construction impact. So that's the reason we started developing this model and using the sediment as a surrogate for impact on mussel. We are looking at how much sediment would be in suspension and how far downstream that sediment would go, and if it's going to be on the bed as a depositional particles, what would be the size of the sediment and what would be the thickness of the depositional area and how far again downstream. So that's kind of a little bit of background about the project. When you're talking about the overland erosion, this is a natural process. When there is a rainfall, if the soil is susceptible to erosion, you're going to see the sediment running over the land, eventually get to the water body. And the forces here we are talking about is rainfall. We are not talking about the wind erosion. This is rainfall erosion happening. And then when you have enough erosive force, then the soil type, soil compaction, texture, topography of the site, the slope, and some other factors would contribute to the overland erosion. So this is a natural process. We cannot get away from the natural process. But then when you look at the construction activity, you're bringing equipment, disturbing the soil through different processes. There are many activities, including clearing the land, dredging, grading, excavation. There are a lot of activities happening up bank, along the shore, and even in the water. And all these activities would accelerate the overland erosion and contribute more to the sediment that would just be translated to impact on habitat eventually. Then, by many DOTs or agencies, is requirement to use BMPs to reduce, minimize, or eliminate all this impact of the sediment getting to the channel. Either you are using erosion control BMPs, sediment control BMPs, or drainage BMPs. But as we know, maybe some of them are working, some of them doesn't work. You know, they may install it wrongly. The maintenance is not there. So we don't know if they're effective or not, but it's still, that's the state of practice at this point. So basically, this is the structure of the model. We had it from day one in our basically paper. We started doing this project. So this is the structure of this is the architecture of the model. The model has three different layers: the input layer, the computational layer, and the post-processing layer. The input layer includes the rainfall data, flow data, construction activity, what type of BMPs that might be implemented in the future, as well as the stream hydraulics and scouring analysis for the specific site. The computational part has two engines. One is the overland erosion calculation that then is going to be linked to the in-stream channel sediment transport model. Eventually, the result would be translated to sediment load and substrate change maps for each day of construction. And then the next step for us is to get all this information, translate it to habitat suitability index, and show basically stakeholders or client So this area is going to have some impact on muscle. This area may have less impact on the muscle. This is more about the computational structure of the GIS toolbar. Here on the left side, we have the overland erosion part. The other side, the right side, the sediment transport, basically model of the GIS toolbar. For the overland erosion, the data that is required for the model includes the basically construction site, where the bridge is located, the time period for each activity, when it starts, when it ends, and then the DEM, what's the DEM for the site, if the DEM is going to change due to the bringing foreign land or removing the native soil. So if the DEM is changed, we have to import this information to the model. And the model uses SCS method to calculate overland flow, calculate the runoff volume and the Q peak, the maximum discharge, using other information from the site, including the CN value and basically other hydrologic parameter, slope and everything, to get the hydrologic part calculating the flow rate. And then it uses the Mussel equation, a modified universal soil loss erosion soil loss equation, to calculate how much sediment is generated over land due to that rainfall that happened that specific day, by considering the C factor, which is basically one of the BMP's factors in this equation, P factor, structural factor, the BMP's, erosivity factor, K value, and the LS, which is a slope factor here, a slope length factor. So the model does the calculation and generate the sediment load per day of the construction. So it's going to be a chart, time versus sediment load per day. And it's going to feed to the sediment transport model here. This is one input coming from inside. From outside, we need to bring the result from a HECRAS study that would include the depth, velocity, and shear stress. And the model would combine this information, going to use the particle tracking method, track all the sediment particles coming to the channel, and track them. Is going to be in suspension, or it's going to be deposited on the bottom of the channel, and how far downstream. So I'm not going to go to the detail of this computational process, but eventually it's going to give us those heat maps for substrate change and heat maps for suspended sediment concentration downstream of the bridge. So for the SCS method, as I mentioned, based on the location of the project, the CN is going to be pulled out from the databases, and then the time of concentration, time to peak, everything would be calculated, and eventually we're going to get two values here, the volume of the runoff for that specific day, and then the Q peak, the maximum discharge. Then the Mussel equation would be calculating the sediment yield, how much sediment in tons per day would be entering to channel. The second part is basically an in-stream sediment transport model, is a particle tracking, is not the traditional sediment transport model. It does not require that kind of calibration we need or validation. It tracks the particle using the advection dispersion equation in two-dimensional domain, track all the particles. If the particle is here, it's going to track this particle, is going to end up on the bottom of the channel, or it's going to be in suspension. If it's end up sitting on the bottom of the channel, is it going to be resuspended further downstream or not? So this is going to be calculating until all the sediments in suspension would leave the downstream domain of the system. So this is the interface of the model. Basically, this is an add-in toolbar that can be installed on GIS Pro. So the user has this key bottom saying that this is the sediment transport model. Clicking, going to go to the next page to enter the data. So the model is developed. We have developed the technical manual along with it, a user manual, and also an instructional video. It comes with all the instructions, how to set up the model, how to run the model, and how to do the post-processing. This is the first page for entering the data, the DM, the CN, K value, and all other hydrological data and soil data are populated for the entire state of Texas. So the user has access directly to the data, and the software does all this work in the background, but it can be populated for other states as well. So DM is there, you just need to locate the coordinate of the site, and then the DM is going to be populated. If the DM is going to be changed during each construction step, you can define the new DM. You may have different slopes during construction, adding more embankment, removing some slopes. So that's going to be DM change. CN is going to be, again, for the native soil, uploaded directly from some databases. But during construction, when you're removing the land cover or bringing new soil, the CN runoff coefficient would change. You go with the CN change data. The erosivity factor would change also during construction, maybe for one of them or two of them or for all of them. Then you can define the new K value to the site. Then you have to delineate the footprint of the construction, showing that this is let's say, watershed, but it's not the contributing area to the overland erosion here. So these are the main parameters that the user needs to introduce. And then the BMPs, if there is a BMP plan to utilize during each construction activity, we have a drop list for different BMPs, structural BMPs, management BMPs. They can use them. If they know if this BMPs has certain efficiency, they can enter the efficiency between 0 to 100%. If they don't know, we have some default values based on the previous research. They can use the default values. The other information that is needed is the construction activity. How many construction activity you have? What is the day one? The construction start was the last day of that construction activity. So there's a planner the user would use to introduce the construction activity. The second part is the information that is needed for in-stream sediment transport. Mainly the information would come from the HECRAS 2D, and there are 3 different parameters is required: flow depth, shear stress, and flow velocity. These are the places that the user would upload the data from the output of the HECRAS 2D. And eventually the sediment source, if the sediment is coming at one corner, is this point source, or is coming across the channel or along the channel. And if it's coming across the channel, we have to define the width of the channel to the model, so model would do the rest. There is another tab for the scouring. If there is a scouring analysis done for this specific bridge, the scouring would be another source for the sediment. So based on the type of the scouring, number of the piers, so the user would enter all this information, and the model does the calculation for how much volume of sediment would be generated from the scouring, would add to the model as another source. So it's good. You have an overland erosion, one source, scouring, another source. So the data that is needed for this model, some of them are manually introduced to the model, some of them are automated, as I mentioned. The DM is automated, the CNK, these are all the information that is already incorporated to the model. But if the DM, K, and CN value is changing, as I mentioned, the user needs to introduce those information. BMPs should be introduced by the user. And also I mentioned the flow data as well as location of the sediment source. So these are the information for the state of Texas. It's already included in the model. Here you have see the DM. Here we see, I'm not sure which one is this one, curve number CN, and this is the K value. This is very tiny. On top of this information, we added 2 more information here. We have the stream segments for the entire state of Texas. Based on the DM, we could not locate the exact point source. So we added this layer to make sure that when you define the point source is inside the channel, it's not outside. And then we have the road inventory for the entire state of Texas again. If you have a footprint of the bridge, if you have a road, a pavement, the CN value and K value would be different from what we can pull out from the other sources. So that's some sort of the superseding those information to make that type of correction. This is one example of the this toolbar we implemented for one site in northern Texas. This is the footprint of the construction activity in Wilson Creek near the McKinney in Texas. North side, south side, this is the area of the footprint. And then here we can see, I don't see it myself from there. It's too tiny. Sorry about that. So I can guess this is the CN value, yes. And that should be the K value. And this is the VN. And the other information basically that model would generate is the flow accumulation. So we have this footprint where the flow goes. It goes this way, that way, or just end up the channel. So flow accumulation is generated by the model. And also the flow direction, how much flow is going this way or the other way. So these are the background type of calculation. User does not need to do anything with this. This is the date picker, basically, start date of this construction activity. First activity, for example, starts in this case, 1st of June, and then ends. We can pick a date, 10 days later, 2 months later, whatever that date is. So, and what type of activity you have, if there was any BMPs or not, is a structural BMP or management BMPs. So these are the drop-downs and the selection for the BMPs for both structural BMPs. It could be a slope bench, it could be phasing, it could be a silt fence, all kind of the structural BMPs. For the land cover BMPs or non-structural BMPs, we can use the hydroseeding, mulching, turfing, those kind of the non-structural BMPs. So the user can select either of them for each construction activity. So this is the data we pull out from the HEC-RAS 2D to bring to the model. Model does not do the hydraulic calculation, but it does do the sediment transport calculation by using the flow depth, flow velocity, and shear stress for the entire study area. So this is the information as in the 2D domain. We can bring it from HEC-RAS 2D or any other 2D model to this GIS toolbar. So basically, we wanted to validate or evaluate the performance of our model. We were fortunate to get at least one site. We were looking for more, but the schedule for the project didn't allow us to go for more sites. But we did the validation of the model by using 3 different methods. We had some laboratory data for sediment transport. So we validate our sediment transport model with the lab data. We had some numerical model result. We validated our model based on that. But the core of this validation was running this model and compare it against the field data, which is the more acceptable, basically, practice. So basically what we did, we collect data at this site. As I mentioned, this is the Wilson Creek Bridge. This is the footprint of the bridge. We collected many data, many sets of data there. We look at the stream bank erosion by putting some erosion pins, and then we go there quarterly, measure that how much the stream is eroded. We did some surveying, geometry of the channel surveying. We went there quarterly to measure the new geometry. We did the overland erosion, basically field monitoring. We installed 4 erosion plots, 10 by 10 foot plots. And then whenever there was a rainfall, we went out there, we collected how much sediment was eroded within the plot. So we measured the weight, do the gradation. So that was the overland erosion monitoring. We collected sediment, total suspended solid, and turbidity. These are the sites. We had 2 automated water sampler here upstream of the bridge, downstream of the bridge to see, the impact of the construction before the construction, upstream, the downstream. And then within the construction area, also we collected graph samples versus the turbidity data. Also, we collected the bed load by installing the sediment trap downstream to see how much bed load is escaping from the construction area, how much bed load is added to the actual bed load in the channel because of the construction. Also, we delineated the substrate area before the construction start and during the construction to see if you are adding more sediment to the channel on the bottom of the channel because of the construction. And eventually, we did some flow measurement and discharge measurement at this site. We had the 1-year window to do all these monitoring activities, starting from December 2020 to 2021. We collected all these information, as I mentioned, but on top of that, we also documented all construction activities. When this activity started, when the activity ended, and then what type of BMPs they used, because we wanted to mimic the exact construction activity and then run the model for the same activities, compare the result to make sure that we are not missing out anything. So these are some of the examples for different activities. For example, they started site clearing February 1st, and they finished it March the 10th. They had silt fence on north side of the bridge construction site as a BMP. So these are examples that we documented, and then we use all this information to build the GIS model for that specific site. These are some activities that are showing here. We also needed to delineate the footprint of each activity. Some of them have a larger footprint. For example, if you're doing the site clearing, basically you're just disturbing everywhere. If you are doing access road, for example, temporary access road, you have less of footprint but more change in the elevation. So DM would be significantly different when you have an access road going from the up bank to the edge of the stream. So we basically documented whatever was happening at the site for the entire 1 year. So these are some examples of the change in channel geometry. There are some erosion, as you can see, happening on the left bank upstream, and also some deposition left bank upstream. The blue one is the original channel. The green is after 1 year, so there was some deposition on the left bank upstream of the channel. There was a lot of erosion on the left bank downstream of the channel, so we documented all this information. This is showing some TSS, total suspended sediment data we have collected, and then we put the labels here for different activities. So you see there are some activities with less effect on TSS. There are some activities with more effect on the releasing suspended sediment. So we basically documented all this information as well. This is the same set of data, but it's the turbidity. It's showing the change in the turbidity. Basically, upstream, the section 1 is upstream, the green one, no impact due to construction. Then we have, in the middle of the construction zone, the black one, you see the turbidity went up significantly. And then further downstream, section 3, the flow gets diluted, sediment would be more or less in suspension. You get back to not exactly what happened before the bridge, but at least you have some dilution here. These are some examples of the positional area. The location basically was bedrock when the construction started. There was no depositional area, there was no gravel, sand on the bed, it's purely bedrock. Then you can see a lot of sediment was sitting down here close to this bank. Further downstream, a lot of sediment were sitting here. So these are all the positional area. Sediment fell down from the overland erosion and then was transported. The coarser one deposited right away. The finer one went downstream. Some of them deposited. Some of them even further downstream got deposited. So to evaluate the performance of the model, we went through 2 different processes. We wanted to evaluate the model in absence of any construction activity and also with the construction activity. Without the construction activity, we validated or evaluated our model. Again, there are 2 separate models, overland erosion and in-stream sediment transfer model. For the overland erosion, we set up the model for the entire year without any construction activity, but the same duration for the construction. And then without the BMPs, and then we ran the model. And then we look at the result for the 1 year erosion day by day. We add them together, sum up, and then we compare the result with two different things. One, with the UCell method. This is the second version of the the first version of the universal loss equation, soil loss equation, which gives us the annual rate of sediment, not the day by day. This is not the event-based method. So when we compared this result, we were confident the model does a good job, and also we compared our result with what we collected from our sediment plots. For the in-stream sediment transport, as I mentioned, we look at the lab data, we look at the numerical data from different sources, as well as running the model for two different cases. One, if the sediments come from upstream, the general sediment transport, and also if sediment coming from the nearby of the bridge area, and then we saw a good result for this model as well. But the main part for our model evaluation was looking at the width construction. So we mimicked the exact, okay. It's good, yeah, it's good. So for the width construction, we simulated the entire construction area for 1 year again, with defining all 10 different activities and also all the BMPs. So these are the activities that we saw. So the actual construction starts from February 1st. By the way, I have to mention that this is the road expansion and bridge replacement. There was already a 2-lane road there and 2-lane bridge, and then they were replacing with the 4-lane road and 4-lane bridges. And there are 2 phases. Phase 1, north lane. The second phase, south lane. So we had the chance to just work on the north lane. The construction was only 1 year. They finished the north lane end of 2021, so we captured the entire activity for the 4th lane. So these are the activities we introduced to the model. And then we had to change the K value, CN value based on different construction activity. We did all this manipulation. We introduced the footprint of each activities. And then, so this is the result for overland erosion. As you can see, we had the data for the rainfall. So by the way, let me go one step back. So the erosive force here is the rainfall. So the way the model works is when you're locating or introducing the location of the bridge, the model is going to search and find the closest rain gauge station with the minimum of 50 years data, and then would generate the rainfall for the future for each day of a construction. So the synthetic rainfall is generated for the future bridges. In this case, we already have a bridge in place, and we have the monitoring duration. We want to use the actual rainfall. So we use the actual rainfall from the close by station, which is Frisco. These are the actual rainfall data. And these are the produced overland erosion sediment yield from the north side of the bridge and south side of the bridge, and the total. This is a comparison between two results, without the bridge, with the bridge, during the different activities. As you can see, the highest overland erosion we got is about 13 tons per day, compared to the 10 without the construction. There was on average 30% increase in the overland erosion. For that specific day, overall, it was less for 1 year. So basically, we picked that day, which is April 29, with the highest contribution to the overland erosion, and we look at the downstream sediment regime, and then also we look at the low flow condition with the low contribution to sediment. So we picked another date, which is November the 3rd. So the result is basically, these are the results. So this map shows how sediment would be distributed, sediment suspension downstream of the bridge. Obviously, the highest contribution or concentration would be at the sources, left and right, and then as sediment transported downstream, the plume is transported downstream, it's going to be diluted. So section 1, 2, and 3, you see the sediment is not uniformly distributed. We have values from 5 to 30 milligram per liter. As you go downstream, the maximum is 3. More dilution happens at section 3. Then we get to the almost background. So that's basically gives the text out. How far downstream you may see your effect because of the bridge. This is another result, but same result, but the cross-section very close to construction activity. The numbers are significantly high when you're at the construction site, but when you go further downstream, you don't see much of the effect. This is showing where the sediment would deposited along this study area. This is the area that the more coarser material, gravel and coarser, deposited, and the model basically showing that. The green dots are where the sands deposited, the prediction, which matched very well with the observation, and then we have the clay depositing along the sides. So I'm going to go, so this is for the low flow condition. I'm not going to talk about it that much, but in conclusion, basically we have developed this toolbar to be used to predict how much sediment can be released during construction activity, how far downstream would go, what would be the thickness of the depositional area, and what would be the length that you see some effect. The results are promising, but we only had one site to evaluate our work. Again, this is an interim product. It has not been adopted yet by TxDOT. The next step for us is two things. First of all, make it a little bit simpler. Rather than using 2D HECRAS, can we do it with 1D HECRAS? So obviously at the planning stage, you don't have the HECRAS 2D for all the bridges, but you may have HECRAS 1D, which is much simpler. That's the first task for us. The second one is testing this tool at 6 different sites with different hydraulic and geomorphology setting and different bridge sizes. And that's the end of our presentation. Thanks. And if there's any question?
Any questions? Time for maybe one.
Yes.
Your input parameters from HECRAS for shear velocity and depth, that's for, I'm a bit confused as to for what discharge. The discharge that we think might happen, a 2-year, a 10-year?
That's up to the user. So let me go one step more back. So for the rainfall, the model selects basically 25 percentile, 50 percentile, and 71 percentile to generate the result by itself. The user does not need to define them. So there are 3 different scenarios that may happen, right? So for the flow, it's up to the user to decide. Are you going to be the mean flow, maximum flow in terms of let's say 50 year plot, 20 years plot? It depends on the size of the bridge. You may decide which return period to use to run the basic hydraulic model. So what we did, we just, in this case, we did for the actual flow for different low flow, high flow cases.
All right, round of applause. All right, that concludes our session, so good night. Thank you.